Very warm welcome to you wherever in the world you are. This is the fourth installment in our series of OpTek webinars, and the focus for today is microfilters and porous membranes. A quick note before we get going, this session is being recorded and we have set aside time at the end for your questions. Please send them in whenever a thought strikes you using the question box in the upper right-hand corner of your screen. We'll gather them as we go and work through as many as time allows once the presentation wraps up. A little about me before we begin. I'm Alan Coleman, your host for today, and I look after QHSE while also serving as UK Site Director here at OpTek. I've spent most of my career in the semiconductor world, working in both the UK and overseas, with my time spent across equipment engineering, sales, and commercial development. More recently, before joining OpTek, I was QHSE Director at a hand tracking and haptics company headquartered in Bristol. Let me set the scene with a brief picture of OpTek before we dive in, so you know who we are and what we do. We're a global supplier of precision laser processing solutions. Our home base is in Abingdon, Oxfordshire, but our reach stretches well beyond it, with further sites in Greenville, South Carolina, Boston, and Dongguan, China. Abingdon is where our machine builds, micromachining, and R&D all take place, while our fiber center of excellence sits over in Greenville. From the Abingdon site, we design and supply bespoke laser processors and systems able to machine a remarkable spread of materials, from hard ceramics and polymers right through to the most delicate organics. Put simply, if something can be made, there's a good chance we can machine it. Our origins lie in optical fiber processing, machining end faces, removing cladding, and carrying out the kind of fine precision work that lifts both yield and optical performance. That, though, is only the beginning of what we're able to offer. We support the whole arc of laser processing, from on-site services through to guiding customers as they move from R&D and prototyping into full production. Features below 300 microns are everyday work for us, and we offer a clear route from early process development all the way to custom automated systems. Those systems span the full range from compact benchtop units to multi-ton, multi-laser platforms working across 5 axes, with the heaviest weighing in at several tons while still holding sub-micron precision. Our Greenville site in South Carolina is home to the Fiber Center of Excellence, where the focus is advanced fiber optic processing and assembly. The team there builds and delivers precision processors for stripping, cleaving, lensing, and splicing optical fibers, as well as fabricating and aligning optical fiber arrays. Greenville also drives process development, prototyping, and production for customers across the telecom, medical, defense, and sensing markets. And it gives our North American clients local system integration, training, and technical support close to hand. Belonging to the financially strong Humanetics group gives us the footing to commit to ambitious, far-reaching projects. We're also proud to hold a robust set of accreditations, among them ISO 9001, ISO 14001, and ISO 13485 for medical work at our UK and China facilities, each a sign of how seriously we treat quality and sustainability. Microfilters and porous membrane structures sit right at the heart of how advanced medical devices, diagnostics, fuel cells, and the newest energy technologies perform. The catch is that producing precise, repeatable pore geometries at production volumes remains a genuine manufacturing hurdle. To walk us through it, I'm pleased to present my colleague Graham Rutherford, Global R&D Manager here at OpTek Systems. Graham is going to take you through some of the most exciting progress and capability we've built up in this area, and I'll be back at the close to host the question and answers. With that, I'll hand you over to Graham.
Okay, thank you for that, Alan. Yes, just to introduce myself. So I've been working in the laser industry since about 1996. Started out as a laser engineer working in the lab on new applications. I've been at OpTek for the last 19 years, and over that time, I've helped to build up a team of really excellent R&D engineers and technicians who are capable of developing new processes from concept through to subcontract manufacture. Often we hope that this leads on to the sale of fully automated production systems. So we've always got that in mind when we're developing a process. So we make sure that things can be advanced up to higher manufacturing rates in the future. So today we're going to be talking about micro hole arrays, What are they and why do we need them? Well, typically we can machine holes very, very small, so between 1 micron and 1 millimeter in quite large arrays. So these can be used as filters for very precise applications, sometimes for the medical industry and sometimes just for sort of the energy for batteries and fuel cells, that type of thing. So for these particular very small holes on a very close pitch, lasers are particularly good at this low end of the scale. And we'll go through why we have that advantage. It also means that because we're using lasers, we can machine basically any material, and that might be difficult to do mechanically. So we'll start by discussing the challenges with making a good filter, why lasers are a good way of solving them, and then go on to look at some case studies to demonstrate what can be achieved with the latest technologies. So there's a growing demand for precision filtration in the market. So these can be for many reasons. So obviously clean manufacturing, lots of stuff needs to be done in clean rooms now so you don't get any contamination. So laser processing is very good at that. Liquid biopsies and cell isolation is another application that we've been involved in. So that's going to be one of our case studies, as in industrial processes to do with, as I said, battery manufacture and fuel cells. We've also been involved in sort of medical device miniaturization, and bioprocessing and cell therapy growth is another market. So what are the key challenges? So consistent pore geometry, so getting the size and the shape and the spacing must be tightly controlled. So that's to do with the hardware as well around holding the part, as well as the actual laser itself. So we'll talk a little bit about that. High flow rates are important. So what's the open area of the filter? So how much can you get flow through? The danger with the very high flow rates is that you lose mechanical strength. So minimizing any damage to the web that holds the filter together is very important, and to prevent tearing, cracking, and deformation. Choosing the right materials, so biocompatibility. So like I said, we can machine many different types of plastics and keep stable processing without having any contamination or material changes. And we have the techniques to manufacture at scale, take things from the R&D stage on to production. So why use lasers? Well, there are various problems with chemical etching and mechanical drilling that we can solve. So often mechanical drilling is difficult to get the very small sizes, so there's a limited to the resolution, and any toolware that you might have will change that hole size as you progress through the filter manufacturing process. With lasers, we don't really have that problem, so we can have like I say, hole sizes down to 1 micron and very precise accuracy. And once you've found some laser parameters, they don't tend to change over that process, so you don't have any problems with the toolware. And with chemical etching, you do get issues with undercutting. They tend to have a bit more variability when you go below about 50 microns. And you might have more taper on the holes, things like that. So, and the main problem with chemical etching is that you often need to produce a mask in order to generate the pattern. So there's like multiple steps in creating that array of holes. Whereas with the laser processing you can just change the design on a bit of software and then you're ready to go and make the next filter in whatever complex pattern you might want to do. So the takeaway from that one is that we can create high density arrays with very repeatable performance. This is just a slide to demonstrate a little bit more some of the things we've been talking about. So the pitch spacing is obviously the space between the holes and the hole diameter, and those two things together go to make up the mechanical strength, as well as the open area. And what we're able to do is obviously create very tight control on the hole diameter. The thickness will make a difference on this. Obviously, the thicker the material, the more robust, but it will take longer to machine, and it will get harder to do the very smallest holes in thicker material. But apart from that, we sort of work in a range of 10 microns up to a millimeter, something like that, depending on the application and the speed of processing. And one of the key aspects that you can do with a laser is the surface finish. So you can get very smooth surface walls to the holes, which allows for good flow characteristics through the filter. I'm just going to talk about the complexity of choosing the right laser. So over the years, there's been many types of lasers designed, ranging from gas lasers like the EXMA, solid state lasers, which broadly covers the femto, the fiber, and the diode pump solid state. And then you've got CO2 lasers, which have been around for a long time for sort of general purpose cutting requirements. So the wavelength range can be from the deep UV with the EXMA lasers right through to the far infrared with CO2 lasers. And the pulse widths can range from femtoseconds, so 10 to the minus 15 seconds, to microseconds, meaning that you could have one laser will have a pulse width over 1 billion times longer than a different laser. So getting those parameters right can be quite tricky. But by picking the correct laser, we can match the laser wavelength and the pulse width to the material to achieve the optimum absorbance and the heat flow characteristics needed. Also factoring in the process times required. There's often a compromise there. So using the correct laser will provide the fastest processing speeds with minimal heating effects and the highest yields. Typically, we've been using fiber lasers for this work because they are more precise than CO2 and cheaper to run than EXMA lasers. Note that all fiber lasers work by generating in the infrared wavelength, so around about 1 micron. So this is the cheapest and the highest power option of the lasers. And other wavelengths are created by passing the infrared light through a nonlinear crystal. This can halve the wavelength of the light, improving its ability to be absorbed, but reduces the power by around 50% as well. And obviously the price goes up because of the added complexity. So a universal requirement for all our customers is wanting to process parts as fast and cheaply as possible. Most of the work is done with pulsed lasers, and here the pulse energy is what controls the process in general. So if we can speed up how fast we can deliver the pulses, we can speed up the process. But this will also increase the average power of the laser. So we have to be careful about overheating. The good thing about doubling the power of a laser is that you don't necessarily double the cost. So you can get a saving from that point of view. Now, older diode pump solid state lasers, just to sort of talk through how lasers are performing work in general. So they're older technology, but we still do use them because they have advantages in terms of pulse energy, pulse shape, under the right circumstance. So these lasers took over from the older style lamp pump lasers from the last century. So in this design, the laser medium is a solid crystal, so that's the laser rod in the description. This is energized by pumping it with light from the simple laser diode. So this laser diode here would be relatively inexpensive, but produces low quality light, but of the right wavelength to excite the laser medium. This then re-emits that light in the wavelength of light that you want, and is a coherent beam as you would expect from a laser. This is the next generation of the lasers. Fiber lasers have largely taken over. They continue to dominate the markets, mainly through marking applications, but also through micromachining. Most of these lasers operate in the nanosecond regime with the base frequency. Here we need to know how well the radiation is absorbed into the material, as well as so choosing the right wavelength is important. So if we looked at the graph on the bottom right there, you can see how different materials are absorbed differently with different wavelengths of light. So, for example, you can see the gold line, which is this red line, is not very absorbed very well. So the red infrared wavelength is not absorbed very well, but the green wavelength is absorbed at 30%, and at the UV, you're probably going to be getting more like 60%. So choosing the right wavelength of light is important when you know what material you're using. If you look at the iron line, for instance, then green and infrared is very similar, so you might as well use the infrared laser as it's cheaper. The market is demanding higher powers, so parts can be processed quicker and cheaper. This is driving the need for higher speed handling equipment like galvo scanners and parallel processing methods. And the other good thing about fiber lasers is that they require little to no maintenance. and they have higher reliability than diode pump solid state or lamp pumped lasers. So we're just going to look at the difference between ultra-fast lasers and standard fiber lasers. So ultra-fast lasers will still start out with a fiber laser at the beginning, and then there are multiple optical elements in between, which would then shorten the pulse down to picosecond level, 10 to the minus 12, or femtosecond level, 10 to the minus 15. So when you machine with a nanosecond laser, you have a relatively long pulse, 10 to the minus 9 seconds. This length of pulse allows the light to soak into the material as such. So you'll have a period in the center of the spot where you have ablation, which is where you just completely destroy the bonds between atoms and the atom is vaporized. But because you have that longer pulse, you also have a melt zone that's created during the lifetime of the pulse. So when the ablated material is removed, this melted metal would then be exploded out of the hole, leaving damaged surfaces, ejected material, and when that melted zone then re-solidifies, you can end up with micro cracking. So that's the disadvantage with a nanosecond laser. The advantage is it's can be much faster. Now, when ultra-fast laser pulses interact with the target material, the result is non-thermal absorption of energy. And this is possible because ultra-fast pulse durations are shorter than the characteristic time of vibrational relaxation in the material, allowing energy to be deposited faster than it is dissipated. So this cold process removes the material with virtually no heat transfer to the surrounding area, dramatically reducing melting and recast material as well as microcracks. The resulting surface quality is higher than what is possible with nanosecond lasers due to a significant reduction in heat-affected zone, debris, and surface damage. As you can see from the picture here, you'll be delivering one nanosecond pulse when you have many femtosecond pulses going in. Femtosecond pulse lasers tend to run at higher rep rates. So although you might get less material removed per pulse, you're able to put more pulses in, and you can either do things like have trains of pulses, which can improve your throughput. So in order to get the fastest processing of your product, you need to be able to drill multiple holes within a second. So you can either do this by moving the part around using XY stages, or you can use a scanning system. So there are multiple scanning systems available. You can have a 2-axis scanner, which effectively is 2 moving mirrors that steer the laser beam, or you can even have more complex scanners like multi-axis scanners or polygon scanners, which we'll talk about in a little bit. The other option is to split your beam into multiple beamlets, so you machine multiple holes at the same time. So you can do this with a diffractive optical element or a spatial light modulator. So this slide is showing you the different effects from the galvo scanning system. So on the bottom left, you'll see that the beams coming in from the right-hand side of that picture, there's a focusing lens, and then the focusing beam is steered around the part using 2 movable mirrors. So each mirror in the X, one for the X, one for the Y, is on a motor, which is then controlled and can steer the beam around. The moving lens is so that it keeps the focus of the laser in the same place, so you have a flat field. There are other methods of doing this. You could just have a more simple scanner that only has 2 axes, but then it has a more limited field of view. So there's pros and cons to different methods, and that's what we're here for, to advise on that. There are more advanced galvo scanning systems. So that's the blue device top left. So they're much bigger devices. They will have multiple axes in there, and that allows you to have full control over the hole that you're creating. So in the top middle, you can see the entrance side of an array of holes where all the entrance sizes are the same. And the image below that is a view of the exit side, where you can see that we varied the size of the exit just by changing the software in the scanning system. So you can make the exit smaller than the entrance or larger than the entrance or parallel. So which you can see in the top right there, you've got cutting examples. So you could have a parallel or straight wall hole, an inverse taper, or even a filleted straight wall, so you can have a funnel shape going into the hole, and everything in between using the custom function. If you really want to machine multiple holes at the same time, then you can use a diffractive optic element. There's also a similar device called a spatial light modulator, which will do the same job in a slightly different way. So you would have one beam coming in. The optic would then split that beam in up to sort of 25 different holes, say, and then you can still use the galvo scanner to then steer that pattern of holes around your part and just drill 25 holes simultaneously, move to a new position, drill another 25 holes. Just as an aside, you can also use this technique to create lines or riblets in a material as well to get textured surfaces. So now we're going to talk through some of the case studies that we've developed here. So first of all, we're going to talk about circulating tumor cell isolation for the biomedical industry. So we've been drilling arrays of over 250 million holes in a piece of PET material, which is around sort of A4 to A3 size. So this application involves drilling 6 micron holes to an accuracy of plus or minus 0.5 microns. So this allows you to capture cancerous cells because they are stiff and unable to get through that size of hole, but healthy blood cells are more malleable and then will be able to squeeze through the hole. So in this way, you could put a cancer patient on dialysis, filter all the cancer cells out of the blood, and then either use that for diagnosis or do this as a regular dialysis operation and just clean the blood and take all the cancer cells out and then put it back into the patient. So these particular samples were done by using a nanosecond laser. It was possible to drill each hole with a single shot, which meant that we could drill at 30,000 holes per second. So we've also demonstrated this process in lots of different materials. So you can also process ePTFE, polyimide material, ABS, and many other types of plastic. And the cutting rate mainly might change slightly depending on the plastics, but it's not too much different. But obviously the thickness has a much bigger effect on the cutting rate in this case. So in order to improve that processing speed, you can see what we did in the lab was we started off with a fairly manual process. We would load the material onto an XY stage and scan the part underneath the laser beam. But in order to do this in production, we needed to automate it. So the machine that you can see running on the right-hand side video is creating smaller patches of those arrays of holes for diagnostic purposes. So this wouldn't be used for dialysis. You take the blood out and then you run it through this filter and collect all the cancer cells to determine what they were. So in this case, you've got the galvo scanner, which is the device with the red ring on it, produces the holes. The next station examines the holes and measures them all to make sure they're correct. The system will then determine is it's pass or fail and will then mark the plastic material with a data matrix code or cross it out and register it so it can be thrown away at the end of the process. Automation has always been a feature of OpTek machines, and in recent years the level of automation has increased. A lot of this is driven by our use of AI. One of the benefits of automation is not just that it can be unmanned, but also it can be done as part of a lights out operation if you put all of the inspection into the same process. So often can reduce parts costs in that way, as well as by speeding things up. On a related topic, so this isn't directly to do with machining the filter itself, but a lot of the filters will need precision marking for the medical industry. So the device on the right-hand side there is a filter housing. It's of a particular plastic, which is difficult to machine with traditional marking systems. So we had to develop a process that would work with that plastic, and we've sold several machines that are clean room compatible. That could be put on a production line. You would simply put the part in, the machine would identify which filter housing it was, It can then position the part correctly so that it puts the mark in the correct place, puts the mark on, writes the data matrix code, then uses a camera to re-examine everything it's written, and then if it's acceptable, it would pass that or fail that at that point. So in addition to be able to mark these sort of processes, you could imagine this could also be a particularly complicated shape of filter. So we could also be drilling the holes in a part that was this sort of shape as well, and using a 5-axis CNC, always have the holes perpendicular to the surface and that type of idea, get the orientation right. The next application would be for high porosity drilling for energy applications. So this could be things for batteries, for the electrodes in batteries, or as a support membrane for fuel cells. So the high-speed drilling of high-density holes in supporting structures for the next generation of fuel cells. This allows complex chemical slurries to be supported by a membrane that allows gases to penetrate through the barrier. So you need to be able to have a relatively strong, stiff material. The slurry would then be coated onto the substrate, but you need to have it porous so that the gas can go through. So the integrity of the membrane is very important, and getting the pitch close so you have a large open area. And obviously, because it's going into production, then the drilling the material needs to be fast enough to meet the price targets, but it also needs to put in very little heat so you don't end up with distortion of the metal substrate. So as you can see from the drilling pattern that we're doing there, we're not just drilling the holes one at a time sequentially, we're actually drilling layers of holes, changing the position and spreading heat around to try and stop any distortion happening. Finally, we're going to talk about the aerospace industry and last chance filters. So these are used to catch any large particulate debris that may have got beyond the original fuel filters. They're often placed just before the engine. That's why they're called last chance filters, to make sure you don't get any large items of debris getting into the engine and causing scoring or damage of the engine itself. Because they have to cope with very high fuel rates, they're often slightly thicker materials, up to 0.5 millimeter thick, and because they need to be able to cope with very high pressures. They need to be suitable for bidirectional flow applications. They have to have high strength, obviously, and be very puncture resistant and fatigue resistant as well, because they have to last a very long time. So hole sizes in here can range between sort of 40 microns, 150 microns, and probably higher than that. We've seen some go up to 450 micron hole sizes, and we've had some filters ranging down to about 15. Well, that's a little bit on the small side. Because of the thicker material and the need to make these components cost effectively, we use a nanosecond laser in the infrared. That does to create more burr even around the hole. So as you can see, these parts don't show any of that because they go through a chemical etching process afterwards. And that removes any of the debris and burr that might be created by the laser process and make sure that all the holes are clear. And because this isn't a medical application, there's slightly larger tolerance on the hole size on these ones, which is why we're able to do that chemical processing to the part. So in summary, we can do any material, so be metals, ceramics, diamond, plastics, anything that needs holes drilling in it is not really a problem. It just comes down to the speed. That's where we come in developing the process to make that as fast as possible and still within specifications. We can do very small sizes, and we can pack those holes very closely together and retain the strength of the webbing so we can have a large open area. And altogether, it's a very precise and repeatable process, which can be monitored throughout with active monitoring of the power and beam quality if required. So why choose OpTek Systems? Well, we're specialists in laser micromachining. We've been doing precision fiber processing and micromachining for small complex components for many, many years. We have decades of experience developing bespoke systems to very exact technical requirements. We offer both standalone systems and fully integrated manufacturing solutions. So we could build a module that goes on an existing production line, for instance, if that was required, or it could be a standalone machine built to safety standards. We have in-house applications labs here, so we can take everything from consultation through to process development, prototyping, subcontract work, and then onto machine sale if required. And as Alan said, we have the necessary industrial certifications for medical devices in the UK and China, and we have ISO 9001 all throughout our business. So thank you for your attention. If we just hand over to questions now with Alan, that'd be great.
Graham, thank you for such an absorbing and insightful talk. It's a real pleasure to see the level of innovation and capability our team at OpTek brings to the table. So we'll get started on some of the questions. We've had a few come in. So the first one, Graham, is what are the biggest challenges when scaling from prototype to production?
So mainly it can be very easy to drill the perfect hole very slowly. So we probably often do start off with that, but have it in mind that how are we going to scale this up? So because it's no use just being able to do it in the lab, you need to be able to do it in reality at a cost-effective speed. So what we might do in the lab, we then also have to have in mind what hardware are we going to use to move the beam around, create more spots, or just move the beam around quicker. So that's kind of the biggest challenge is knowing where you're going to at the point where you're developing the process.
Fantastic, thank you, Graham. So next question in, did you say 30,000 holes a second? What's the thickness of the sheets?
So yes, I did say 30,000 holes per second, so it is pretty fast. The thickness of that sheet was only 25 microns. So I wouldn't be able to do 30,000 holes per second in 1 millimeter thick, but it just depends exactly on the hole size, what the material is, and what the thickness is as to whether we could repeat that or not. But yes, it's usually in the order of I think we've done 0.3 millimeter steel, I think 1,000 holes per second, something like that. So yeah, it just depends on the application and what the quality level you need after is depending on what laser you choose.
Brilliant, thank you, Graham. Next question, when would you use an ultrafast laser instead of a nanosecond laser?
Okay, so if we go back to some of the earlier slides, basically if you want a really, really clean hole with zero debris and no melt or recast around the hole, that's when you want to be using an ultrafast laser. But generally, they will be slightly slower and slightly more, and the lasers will be more expensive. So if you don't need that level of precision, then you could use a nanosecond laser that will definitely be faster, and you'll be able to do thicker materials in a sensible amount of time. So you might have to compromise on the quality in order to get the cost-effective throughput that you require for your product.
Okay, fantastic. So next one up, what limits the smallest hole size you can produce?
So the physics of the situation is that the smallest hole you can produce is the wavelength of light that you're trying to send through the hole. So for a 1 micron wavelength, then in theory, the smallest hole you can create is 1 micron. In reality, you can't focus the light down to a perfect spot. So the quality of the optics will make a difference, and the power levels and the heat input into the material will make a difference. So often on the very smallest holes, so down to sort of 3 microns level, we'll have to use a shorter wavelength of light so we can get a smaller spot. And you might find that the entrance of the hole is slightly bigger than the exit of the hole, just because of heat input and things like that. So
really interesting, really interesting. Okay, one more. How do you balance high flow rate with mechanical strength? Interesting one there.
yeah, so this is very much application to application is going to be different. So for high flow rate, you want to put all the holes as closely packed together as possible. So you'd be using a triangular pitch instead of a square pitch. You'd be trying to minimize heat effects into the material so that the webbing between the holes remains strong. So, and there's always going to be a balance. So what we often do is we'll do some tests where we slowly reduce the pitch of the holes until you get to the minimum pitch before that webbing starts to break down. And then we can do some more trials around that just to optimize the process.
Fantastic. We've just had one more pop in, just as we were thinking that was the last question. How do you choose the right laser for a new filter material?
Okay, so again, we sort of touched on this a little bit earlier. So you would have to look at what wavelengths of light were absorbed by that material. So often the metal, it doesn't matter what wavelength you've got, they all absorb perfectly well. But if you have a clear plastic and you've got a wavelength of light which is not visible to the human eye, so it's like a near infrared, that light then transfers straight through the clear plastic. So what you'd have to do is look at some of the graphs like the ones we looked at earlier, find a wavelength of light that's absorbed well by the material, and then that's a laser you would choose. But then you'd also need to worry about how fast you want to drill. So do you need a nanosecond because it's a thick material and it's a relatively big hole, or do you need a perfectly precise, very small hole, in which case you'd want to be going with a femtosecond laser?
Okay. And the questions are coming in as we're finishing off, Graham. So this is a follow-on from a 30,000 holes a second question. Is the last chance holes a single shot drilling or more?
So the last chance holes can be both. So some lasers will do you a single shot, but then that will be quite messy and there'll be quite a lot of cleaning up to do afterwards. And then the last chance filters that we do tends to be multiple pulses for each hole. But because the lasers are running at thousands of pulses per second, that can still mean that you do several holes per second. So maybe 30 holes per second, something like that for a thicker material.
Okay, fantastic. Well, with no more questions, that brings us to the end for today. We hope this fourth OpTek webinar was time well spent. A big thank you to Graham for such a strong presentation and for so generously sharing what he knows. This recording will be with you over the next few days, and we very much look forward to welcoming you back for the next in our series of webinars. Thank you.